Hi, my name is Sanghamitra Sadasivuni of JIS University from the Department of Earth Sciences. Today my topic of seminar would be phase diagrams associated with Igneous. Now to understand the phase diagrams, we need to understand the phase rule behind it, which was given by Gibbs. The phase rule gives us the relationship between the number of degree of freedoms with the number of components and the number of phases, which is mathematically expressed as P plus F equals to C plus 2, where 2 gives us the two intensive parameters, that is temperature and pressure. Now there are three types of phase diagrams, that is binary phase diagram where two components are involved, ternary phase diagrams where three components are involved, quaternary phase diagrams where four components are involved. Usually the quaternary phase diagrams cannot be done by human, so it is done with the help of computer, and it is also understood with the help of technology and computers. Now in today's seminar, let us confine ourselves with the binary system or the binary phase diagrams. In the binary phase diagrams, we have three subtopics. Those are complete solid and liquid phase diagrams, eutectic diagrams, and peritectic diagrams. Now let us start with the eutectic diagrams. The binary system with eutectic relation. In the system, let us take diopside or northite system as an example to understand the binary system with eutectic relation. This system is a closed system under isobaric conditions, that is under constant pressure, and the pressure here is 1 bar. Now as we can see in the diagram, the diopside starts crystallizing at 1392 degrees centigrade, while anorthite starts crystallizing at 1553 degrees centigrade. Here in this system, we have to understand that the initial melt composition is always equal to the final solid composition. To understand this, let us take a point A with the initial composition. As the temperature gradually decreases, the composition at A starts to decrease to the point B as in the diagram and starts crossing the liquidus line. The liquidus line is a line where when a melt crosses, it starts to solidify. So the composition the composition follows the liquidus path until and unless it reaches the point E, which is the eutectic point. The temperature at eutectic point is 1274 degrees centigrade, and here the entire melt solidifies and also the solid part starts to liquidify as it also reaches the eutectic point. Below the eutectic point it is the total solid composition TSC path, where the entire composition is solid, and here the subsolidus cooling takes place, that is the decrease in temperature takes place and the solid starts cooling without change in its phase. With this system, we can understand the petrogenesis, and we can also explain the formation of textures such as integral textures, which are porphyritic, poikilotic, ophitic, subophitic textures. Let us use the phase rule to describe the binary system. The number of components in this system are two, that is the dioxide and the anorthite, and the intensive parameters is 1 as pressure is constant. Above the liquidus, the number of phases are 2. Therefore, if we calculate it in the Gibbs phase rule, that is P plus F equals to C plus 2, we can calculate the phase degree of freedom, which is 2 above the liquidus, that is bivariant, which means the two variants are temperature and the concentration. On the liquidus or below the liquidus, the number of phases are 2, that is the liquid plus solid. Therefore, the number of phases here is 2 and the degree of freedom could be calculated, and which is 1, that is invariant. Therefore here the temperature is fixed or the concentration is fixed. On the eutectic point, the degree of freedom is 0 as we have three phases: the solid phase, the solid phase are dioxide and the anorthite solid phases, and we also have the liquid phase, and there are three phases and the degree of freedom is 0, so this is invariant. With this, we can understand that the maximum number of phases are developed when the degree of freedom is 0. As we can see on the eutectic point, the number of phases are 3, which is maximum, and the degree of freedom is 0. Below the eutectic point, the phase rule is not applicable because of the subsolidus cooling. The prism region between the solidus and the liquidus can contain numerous horizontal lines, that is, those are the isothermal lines joining the solid composition with the corresponding liquid composition. And these isothermal lines also represent different rock types that which are formed due to the fractional crystallization. Therefore, with this system, we can understand that the magma crystallizes in parts rather than all at once. Now let us study our next system, that is the peritectic system. So before that, these are the few intergrowth textures that have been given. The first one is the porphyric textures, and the second is the ophitic textures. The third is the poikilotic textures, as seen in the thin sections of rock samples. Therefore, now let's study the peritectic system. In the peritectic system, we have the forsterite and the silica involving in the formation of a binary compound, that is enstatite. As the reaction is provided, we can understand that in the system, once the forsterite it forms, the melt is silica rich, as forsterite has less silica than enstatite. At any given point, the crystallization of forsterite continues until the liquid reaches the reaction point, that is I, as mentioned in the diagram, where if we take a composition above the reaction point, then the forsterite doesn't form and the formation of enstatite takes place without the formation of forsterite. To explain this, let's take an example of a composition at F, as mentioned. With the gradual decrease in the temperature, the crystallization starts and reaches the point I, where the forsterite liquidus intersects with the enstatite liquidus, and the phases are 3: forsterite, enstatite, and melt. The already formed crystals of forsterite gets converted to enstatite, and because of the original undersaturated melt composition, some forsterite residuals can survive even after the reaction is complete. Therefore, the bulk composition and completion of crystallization at I comprises crystals of forsterite plus enstatite, and no liquid is left over to proceed with the further crystallization on enstatite liquidus. Now, if we take a composition of L, which is above the reaction point, with the gradual decrease in the temperature, instead of forming the forsterite crystals, the composition starts forming enstatite crystals, and the further crystallization behavior is equal to the binary system. Therefore, here incongruent melting takes place, and this is also under isobaric conditions, which is 1 bar. The calculation of phase rule is equivalent to the calculation of phase rule in binary system. With a peritectic system, we can understand the development of orthopyroxene reaction rim around olivine, as observed in many gabbros and tolerites, can be interpreted in terms of reaction point or peritectic reaction. The mantle of pyroxene preventing olivine from further reaction can enrich the residual liquid in silica and ultimately cause a diversification of magma complex. As in the system, the forsterite has been rimmed by enstatite, we can find the zoning texture or the reaction textures. We can find the reaction textures, which are the corona textures, the rimmed textures. Moving on to our next system, that is binary system with complete solid solution. In this system, albite and orthide is involved, and here occurs the coupled substitution through which the zoning takes place. The melting point of anorthite is 1553 degrees centigrade, while albite is 1118 degrees centigrade. The plagioclase feldspar define a solid solution series with albite and anorthite as end members. The continued crystallization of solid and calcic composition will enrich the liquid in albite composition. As composition of the melt changes on cooling, the earlier formed crystals react with the liquid and become more sodic to maintain equilibrium through reciprocal reaction or exchange reaction between the solid and liquid phases. To explain this, let us take a composition with 50% albite and 50% anorthite, that is the point L. With a gradual decrease in the temperature, it reaches the point P and its corresponding solid crystals are W. As the melt reaches the point Q with its corresponding solid at X, where the liquid or the melt reaches the point R and its initial solid is Y, which is equals to the point P, and R equals to the point W, where the initial melt composition equals to the final solid composition, which is attained at temperature of 1285 degrees centigrade. Here the coupled substitution takes place. The petrographic significance here is the system involves in continuous reaction. If cooling takes place at faster rate, then it prevents the reaction through diffusion between the melt and the solid, and the early formed crystals of calcic plagioclase, that is the anorthite, will be melted or later formed sodic plagioclase, that is will be mantled by the albite and forming the normal zoning. In the reverse zoning results from the influx of fresh magma, that is due to the mixing of magma. The processes here are reversible, but in solid solution, the first series formed liquid on melting has a different composition than the last formed solid. As I've mentioned that y is equals to p, that is at y we have the anorthite, in less content, while at p we have anorthite and more content. So here in this system, the initial composition is not equal to the final composition, and in the peritectic system also the initial composition is not equal to the final composition. Here the zoning takes place and the textures are, the first one is the normal zoning of plagioclase and the second one is also normal zoning of olivines. Now let's go on to the last system, that is the binary system with limited solid solution. If we concentrate on the first diagram, the system, instead of a continuous solid solution reaction, it comprises two solid solution subsystems. The liquidus and the solidus of the alkali feldspar series, which fall to a minimum melting point or temperature at about 1060 degrees. We are considering the orthoclase and albite series in this system. Therefore, if we consider a point A which has albite 32 and orthoclase as 68, the orthoclase rich phase at Y but will finally gain a composition that has a melt along the path YZ. The crystal at Z may experience subsolidus cooling with time and finally meet the solvus at P. Exsolution takes place and exsolved phases have composition P and P'. On continuous subsolvus cooling within the immiscible domain, the compositions of both the phases in the intergrowth change progressively. The crystal temperature of the solvus in dry condition is 660 degrees. The dry condition is the first diagram and the wet condition is the second diagram. Here the wet conditions mean the H2O is introduced into the system. An increase in H2O strongly depresses the liquidus down the temperature scale. Although the position of the solvus crest remains unaltered, that is 14 degrees centigrade, at pressure of 5 kb or more, the solvus and the lobes intersect and instead of a single feldspar at the point M, two feldspar phases crystallize. Water saturated magma of suitable composition crystallizes directly in the subsolvus region to produce two separate feldspars and discrete grains without the formative of stage of perthite. Now again, if we concentrate on the first diagram, due to exsolvus or the formation of perthite takes place, that is the inclusions of any rich feldspar takes place in the K feldspar. If the composition is albite rich, and if the composition is orthoclase rich, then antiperthite texture takes place, that is where the host rock or the host normal or there are inclusions of K feldspar in the Na feldspar. This system is mostly used for the explanation of the formation of perthite systems, perthite texture. As we can see, the first one is the perthitic texture in the microscope. As we can see, the twinning of microcline, and the second one is the antiperthitic texture. So in this way, the phase diagrams, we can study the crystallization of behavior of minerals and the formation of different textures associated with different phase diagrams can be explained, and the degree of variance could be explained with the phases in the phase diagrams. These are the references, and thank you.